All right, so let's move on to our the second half of our exercises for today's session. So in these exercises, we're going to access seismological model data. So again, seismological models are simplifications, representations of the Earth, uh, and often for characteristics of the Earth that are not easily observed. So I'm going to ask May to we've bring up share her screen and um, yeah, that looks right. And then let's go through kind of our four-step process, but this time we're going to apply it to accessing seismological model data. All right, so here we are. We're going to go into exercise 3. And again, we hope that these are exercises you can do on your own computer. May and I will show them, work through them here on the shared screen, but you can perform these with your own browser as we go through. Okay, so first exercise is going to be on accessing fault geometry models. So our we've defined a goal here. We want to download the fault geometry for the Raymond Fault, which is a hazardous fault in the Los Angeles area. There's an image here. This green ribbon-shaped object is a visualization of kind of the end result of the fault that, as defined in the SCEC community fault model. So let's go through our four-step process and by starting with where do we locate earthquake fault geometry models. So maybe you could scroll up a little bit here. We'll look at step A. Um, so researchers can retrieve fault geometry from the USGS and other sources, including SCEC. It's worth knowing there's different types of fault geometry descriptions. Some just define the kind of the surface trace where which is where the fault emerges or is visible on the surface of the earth, but other models, including the one we are after, try to represent a full 3D geometry of the fault, which will indicate the dip and the depth, how far, the near surface and the far surface of the full fault, and how it varies along its extent. Um, so there are a number of places where these kind of fault geometry files can be found. The USGS offers a fault database, and they have fault geometry models for many of these. Their fault database is a collection of quaternary faults, which are faults that considered active in the last 2.5 million years. These are considered significant because they have the potential to generate future earthquakes, and their age represents relatively recent tectonic movement. So here on this next page, we've got some links that provide that will take you to different fault models. So the USGS provides an inventory. There's a fault model database. SCEC has a community fault explorer. Crescent has a community fault explorer. Um, and so here's a map of the USGS quaternary fault database. And so most of the faults visible on that map, it's possible to retrieve fault geometries for them. So for our case, we're going to use the SCEC Community Fault Explorer. So for our first step, we're going to go to this link, the Community Fault Explorer, and and when this comes up, we'll see kind of the interface and the information that we need to provide to retrieve fault geometry. So yeah, let's scroll down. So now we've kind of found a location where we can get fault geometry information. So now we want to specify the specific fault that we're interested in, as well as we're going to kind of describe the resolution of the fault geometry that we want to download. So our goal is to find a fault model for the Raymond fault. Um, so on the Web Explorer, one of the uh, issues or the uh, options it's going to present us with is which version of the community fault model do we want to work with. So this lists some previous versions, but basically the um, most recent, the larger number is the most recent version. So that's um, and the most recent would be considered by scientific consensus the best. So we want to work with the best available. Now, also comment on the preferred. So since these are models and it's really not observation based, often there's kind of scientific judgment required to identify which model is best. Um, the Web Explorer provides a preferred, which is maybe the consensus or is the consensus of, among the participating scientists what the best available model is. But it also provides potential alternatives. So we're going to work with a preferred model. Um, After looking at this form, we can see that it provides a variety of different ways to search for faults by keyword, latitude and longitude, etc. Including but we happen to know the name of the fault that we're looking for, so we're going to search by name. And in the picture, you can see that's an option, search by, and then when you select search by, it brings up a list of fault names, and um, we can search through that to find the Raymond fault. So here on step two, we're going to go search by, and we're going to select name, and we could scroll through the list, or we could go to the drop down that says select, and this kind of is a list of the fault and their names that are enlisted or they're available in this fault model. And we expect to find the Raymond fault on there somewhere. So there we've selected the Raymond fault, and now um, it brings up and it shows us a map view and basically the surface expression of this fault. So this is a hazardous fault. It's some under densely populated portion of LA. So we're hoping it doesn't rupture. But once we've selected that, then there's on the Explorer, we see that it provides some detailed information about the Raymond fault, and it gives us some options that include plot the fault or download it. So let's let's go and view it. May, can we, if we go over, our goal is to download the geometry, but if we select this fault, before we download it, let's take a look at it. So why don't we plot it? And this web browser interface provides a nice interface. And so this kind of ribbon here represents the 3D representation of the fault as defined in the SCEC community fault model. And there's various options here. You can show, typically these fault models are defined triangulated surfaces. And the options here for plotting, you can add seismicity to see if a recent seismicity seems to be occurring on the fault. You can add in or hide coastline and other information. and save the image and distribute it. So it's very nice kind of 3D visualization of the fault geometry. This is the kind of visualization that's capable, but on your own computer, but it typically requires specialized software to uh, plot these fault geometry files in a usable way, like we see. All right, so now we're gonna we've viewed it. It looks like what we want, so we're going to go to the download, and so it presents us with options. Uh, in the presentation material, we talked about the different possible resolutions. The native resolution is always the highest resolution. So in some cases, you may not want this very high resolution. It's too detailed for your purposes. So in that case, you would download a lower resolution. But for us, we're going to download the data and the metadata together. So when we've downloaded, we collected that, click that download, we see that a file has been downloaded onto the computer.
Phil, there's a
Yeah,
question in the chat from Fabian here. Which
sure.
seismicity example, which earthquake catalog is loaded in the CFM viewer?
Yeah, May, do you know, is that which catalog, is that the Hauxen catalog or?
I had to check. There was two.
Yeah,
It was actually merged.
okay. Um, Yeah, Fabian, we'll look into that. We've been the CFM Explorer's been updated recently. We want to make sure we tell you the correct information, so we'll check on that. I think it's the relocated Hauxen catalog. That's the basically highest or the most accurate location um, catalog. Because it's been post-processed. So, okay, thanks. So
One more question from Dewan. Is
yeah,
the fault geometry drawn from seismic reflection traces?
um, potentially. So some where there are good seismic reflection information and that have helped image the fault, that is taken into consideration when developing these fault geometry. Um, but that is part of the kind of the scientific process of developing these fault models. And that's an important kind of activity that happens within the SCEC community is researchers discussing their models and how they're developed. So we could send you to that development group if you have particular questions about a particular fault geometry. Okay, so we talked about retrieving it and downloading it. We defined the data. We're going to download the data and metadata. When we do that, we end up with a file, something like, if you scroll back up just a little bit, it looks like it's a zip file, this cfm.zip. And if we unzip that file here on step D, um, the file would be downloaded to your computer, and you unzip it. It contains two ASCII text files. One is a .ts file, which is a tsur file. That's the actual fault geometry. And the other is a metadata CSV file. So we can open the CSV file with a text editor, or this case looks like with Excel, and it identifies different information, metadata about this fault model. And then when it's possible to open the tsur file with a text editor. And here in step D3, we can see the contents of the tsur file. It's ASCII, it has some metadata at the top, but then it has vertices listed in their points. And so it's quite challenging to interpret this fault geometry. Even though it's an ASCII file, it's hard to interpret that just looking at the ASCII file. So typically specialized visualization software will be used to plot the 3D fault geometry. Okay, so just kind of next steps working with fault geometry models. So there's a number of purposes why you might want fault geometry models. So including, they're used by several of the simulation codes that will be presented later in the workshop. So computational models of earthquake ruptures make use of fault geometry uh, um, to help define the location, the extent of the earthquake ruptures. Earthquake wave propagation simulations often need a representation of the fault that moves during the earthquake. Earthquake rupture forecasts, such as the USGS USURF-3, also use fault geometry to define the location and the potential magnitudes of various earthquakes in a region. And as I mentioned, viewing the geometry files is often takes specialized software. And in many cases, this software is commercial. So it's one reason we didn't ask you to install it. But here are some references or some potential codes that can be used to read and view TSERF files. Okay. So I think that's the exercise for retrieving fault information. We encourage you to expand on that exercise and potentially download fault geometries for faults near you or of interest to you.
Phil, a
Yeah.
question from Fabian in the chat. For
Mhm.
us earthquake rupture modelers, is there an easy way to create an example STL file as used for meshing directly from the SCEC fault geometry model, or would you also recommend the software mentioned?
So um, I I don't know of an existing conversion tool to change from TSURF to STL, but it's likely someone in the SCEC community knows or has such a tool. So why don't we take that as a question that we can follow up on, and I'll contact our fault modelers and ask them if they have kind of recommendations. I'm personally not recommending. I pointed to some, visualization tools for TSURFs. Some, including the first one, GoCAD, I'm aware is a fairly expensive commercial, and that is, a barrier. We don't use that at SCEC um, because of that, because it's commercial. So I'm not specifically recommending that. Okay, well, just to keep us here on schedule, so we get so make sure we get finished here with our last exercise this morning. We're here by the end of our scheduled time. We're going to go on to the next exercise. So this is our in this exercise, we're going to talk about how to access seismic velocity model information. So we've defined a specific goal for this exercise to create a plot that shows the VP, VS, and density values between the Earth's surface and 50 kilometers depth as defined in the USGS San Francisco Bay Region Velocity Model for a site on the Stanford campus. Um, so let's go through our 4-step process here. So the first step is to locate this, where can you get access to seismic velocity models? So there's a significant collection of available models, including from USGS and from other individual researchers and from other seismological groups, including SCEC. So we're on these links here. There's a collection of sources where you can find. There's a USGS Central US, the USGS San Francisco Bay Region. EarthScope Consortium has a collection of velocity models, in some cases global models. So we're going to focus on a regional model, specifically for Northern California, but there are others cover, the full globe. The Crescent community has a community velocity model. They have velocity models for Oregon and Washington. And the SCEC has a community velocity model explorers that provides access to a collection of California velocity models. So we're going to use the SCEC community velocity model explorer because I know that the USGS San Francisco Bay model is available through that. So if we click on that community velocity model link, a web page comes up like this. And what we see are a background map, and it shows the coverage region for the San Francisco Bay velocity model. And so Stanford is the site that we're interested, which is a little bit south of San Francisco, is definitely in this region. And so we see certain selection ideas here or options here up at the top. And so let's go back to the workshop material, and we'll kind of collect the information that we're going to enter into this field, or into this form. So here we are on step B, specifying, what information we want out of the velocity model. So this is going to include which model do we want, what location do we want information for, what format we want to download. So starting with the location, we picked a location which is the Mendenhall Library at Stanford University. The form wants it in decimal degrees. So here's a latitude and longitude for that library. And what we are expecting to see when we do this query, we're going to we want to retrieve a vertical profile. And basically what we're expecting is that these values, the VP, VS, and density, are going to be lower near the surface, and they're going to increase as we go deeper into the Earth. We also expect to see, potentially structural information about the Earth, in particular the MOHO. So the MOHO is the boundary that separates Earth's crust from the mantle, and it's typically identified by a sharp increase in seismic wave velocities. Beneath continents, the MOHO is typically found at depths of 30 to 50 kilometers. So if we query from the Earth's surface down to 50 kilometers, we would expect the model to show us where the MOHO is, what depth the MOHO is below Stanford. As we fill out the form and we make our data request, we'll point out there's two different modes for specifying depth information. It's called depth, which are the depth mode and the elevation mode. In depth mode, zero represents the solid Earth surface. So if you're in the ocean, you're at the bottom of the water. So, and if you're on land, you're at the Earth's surface. And then positive values are down. So if you're 100, that means you're 100 meters below the Earth's surface at that point. There's other ways to specify the request, which is elevation mode. In that mode, zero is sea level, positive values are above sea level, and negative values are below sea level. We're going to use depth mode. It's a little bit simpler. So so if we scroll down, so we see there's other fields. We're going to enter the profile type, the Z mode, and then the various other fields. So maybe we scroll down a little bit more and we identify. So here we are in step B. We're trying to specify the specific velocity model information that we're interested in. So we're going to specify these in the form. We're going to select the model that we're interested in, which is San Francisco Bay. We're going to select a 1D vertical profile, and we're going to select the Z mode, which is using the depth. So we'll point out that when you use the CVM Explorer You don't necessarily have to type in a lat long. You could zoom in on the map and you can click the point that you're interested in. That's maybe an easier way to do this. But we have the location for this particular site, so we're going to type in the lat long. We're going to specify the surface point at 0 and the depth at 50,000 meters. We need to specify a spacing between the points. So we're going to say 10-meter resolution, and we're going to specify the data that we want from the model. We want all three material properties, VPVS, and density. So when we collect that information, this is the information we're going to enter into the CVM Explorer. And once it's entered in, we'll click Extract Data. And so why don't we do that? Why don't we go to the Explorer, May, and go through this process. So we're going to select the, we want a 1D velocity. Maybe we can show May that there are other velocity models available. So if we, in this Explorer, there are models for different regions. These are considered regional models, so they don't cover very large areas, but they are more accurate. They're accurate for the areas that they do cover. So there's a wide collection of models available through this. But the most recent USGS model for Northern California is the San Francisco Bay region model. So let's use that. So then we're going to enter the longitude and latitude of our site of interest. We picked Stanford because one of the SCEC co-directors is a Stanford professor. So May's specifying here the starting depth is 0 and the max depth is 50,000 meters. We're going to have 10-meter resolution. So at this point, we've kind of specified, here's the data that we want. On the map, what we see, it puts a location marker showing the data that it's retrieving is for that site that confirms, south of San Francisco. It looks like we've entered the right site. And now we've got some options. We can plot the data, or we can download the data we see in the plots. But before we download it, why don't we take a look at this information that we retrieved and do a little interpretation. So basically what we're seeing is, in some sense, what we expected from this type of, from a vertical profile and a model. So near the surface of the Earth, we hit the VPVS and density values are lower, but very quickly in the top 1,000 or 2,000 meters, these values rise quickly, and then they extend. The model extends them down, and we see a kind of a sharp increase in all three of these properties at somewhere around 24 kilometers deep. So this is the sharp increase in VS and VP values that represent the MOHO. So this model indicates that the MOHO is represented is about 24 kilometers beneath Stanford campus. And then if we go down further, we see basically all the values fall to 0 at about 45 kilometers deep. And what this means and represents is that the models doesn't define, it basically is defined only down to 45 kilometers. And it doesn't define the Earth properties below that. So if you need properties that are deeper than 45, you would either use a different model, or you combine this model for the near surface and then use a background or some global model to provide material properties below 45 kilometers. Okay, so that's kind of interpretation. We want to look at that, but now it looks like what we want. So we're going to click download, and this will download a CSV file. It looks like this plots it in the browser screen. So this is we see there's a little bit of a header here that identifies the site and the model that we queried, and then a list of depths and the VP, VS, and density values found at each of those depths. So these are the data points that are plotted in the plots that we just looked at. Okay, so May, if we go back, yeah, so um, we did this step B2, and we clicked extract data. We scroll down. We saw that the Explorer provided us a link where to either plot or download the data. We looked at these plots. It looks like it's appropriate information. When you download the data, it will generate a file, something like that. And we can open that CSV file with our and see the data values that were plotted. So this is kind of introduction that gives you an example of retrieving a velocity model information. Please feel free to experiment and work with this CVM Explorer. The vertical profile that we provided is one of the simple plots. You can also do both horizontal and vertical cross sections to show, how the velocity models vary as between geological regions. And another important use of seismical velocity models are for use in earthquake wave propagation simulations. So if you want to do an accurate ground motion simulation for a region of interest, such as LA or Northern California, it's essential to have an accurate seismic velocity model. Because the impact of both the phase arrival as well as the ground motion amplitudes. And at SCEC and multiple other groups, there's ongoing efforts to develop, evaluate, and improve seismic velocity models.
Phil,
If you're, yeah.
Julio asked in the chat if there are 3D models available.
So these are 3D models that we're querying, and you can but to generate, if you want to create let's say a simulation, a 3D simulation mesh or a volume that represents the properties in 3D, you would probably use probably not use this Web Explorer. And so one of the codes that SCEC provides and that is called, that will help you generate a 3D simulation mesh or volume, is called UCVM. And for the ground motion modelers, they will basically install and use UCVM to build their 3D meshes. So we didn't cover that in this tutorial, but the CVM Explorer calls UCVM to generate the plots we showed. And we're actively working to install UCVM on Quakeworx so that on Quakeworx you can generate volumes.
Hey, Phil, I just want you to know you've got about 9 minutes left in today's
Okay.
overall training.
Okay, well, very good. So I think that means we're on time, and we just have a few moments for comments or questions, and then we'll wrap up for today.